Hello and welcome to the first lesson on ellipses. I'm going to start just now by having a look at the start question that I published on the classroom, just for you to have a look at to start with. So we've got these 2 points, A and B, and we were asked a few things about the exact length of the line segment between them, the coordinates at the midpoint, and then the equation for that circle, A and B being the ends of the diameter. So the answers were, if we see the answers pop up, so the answers were root 26 for the exact length of A and B. If we look at the distance in the x direction, there is 1, and the difference in their y coordinates is 5, so we're going to get 5 squared is 25, 1 squared is 1. We'll end up having to square root 26 then. Can't do anything with that. Simplify it further as a square root. The coordinates of the midpoint, so we're looking at the average of the x coordinates, the average of the y coordinates. Average x coordinate then would be 3.5, or 7/2, if you like, 7 divided by 2, and the average y coordinate would be 5/2, or 2.5. So that gives us the first bit to the start of the equation of the circle for part C, x minus 3.5 all squared plus y minus 2.5 all squared. And then this bit here we've got is the radius squared. We got the diameter. Is the length from A to B. That's the diameter there. So if that's the diameter, then half of that is going to give us the radius. So if we take root 26 all over 2 and then square it on the top, that would give us 26. On the bottom, it would give us 4, 26 over 4, 13 over 2, or 6.5. There's the answer to that one. Okay. So what we're in the middle of looking at now, we've looked at the circle. We've dealt with that, and we're just moving on to have a look at the ellipse now. So that's where we are. So we'll be interested in Cartesian and parametric forms primarily to start with. Some of the properties, tangents and normals, we'll say we'll deal with all these conic sections together when we're looking at tangents and normals. Move on. So yeah, just a reminder, all these things are defined by sections of cone. So if we can just slice horizontally, we get the circle. If we slice at an angle, which is like that, we're going to get a parabola. If we slice at this angle, we're going to get an ellipse where it cuts in both places. And if we slice at some angle that is not in the same direction as the axis of the cone, we're going to get a hyperbola. Right, if we remember then from our locus lesson, we had this situation where if you had a fixed length of string and attached it to 2 points and then moved around a circle inside that string, it would give you an ellipse. So the sum of the distances from 2 fixed points gives an ellipse. I do have quite a nice little GeoGebra applet here. Unfortunately, it doesn't work when I try and film the PowerPoint, so I've had to just set it up and show you with it complete, otherwise I'd have been able to move the pencil around and show you all of this, but it does work out quite nicely. The 2 lengths, if I move the pencil around, they always sum to this total distance of 6.5. So where do we tend to meet ellipses? One place is in motion of the planets, or in this case what we got is the motion of Earth around the Sun. So we can see the various different places there. It's not a completely circular orbit that the Earth has around the Sun, and at different positions we get spring or autumn depending on where we are, which hemisphere we're in. So for us at the moment, let's just bring up a screen pointer. So we've just been through the 21st of March. So we've just gone through our autumnal equinox and heading towards the solstice, which will be happening for us on the 21st of June. That will be our winter solstice, summer solstice in the northern hemisphere. And this elliptical motion around the sun is what gives us our seasons and the tilting of the Earth towards the sun at different positions. Okay, it's what gives us the seasons. So let's just have a look at ellipses, and we'll start by just reminding ourselves about the circle. So we've got the Cartesian and the parametric equations of a circle. So the Cartesian equation, just if we got radius 1, centre of the origin was just x squared plus y squared equals 1. If we changed it to be radius r, centre of the origin, it was going to be x squared plus y squared is r squared. And the parametric equations of that simple circle with radius 1 were just x is cos theta, y equals sine theta. All right, thinking about the right angled triangle that we get in there. Okay, we've got 1 is the radius, that's going to be cos theta for the adjacent, and that's going to be sine theta for the opposite. So that's what we've seen already, Cartesian equations. If we though start to think about our ellipse, and we're going to let our ellipse have an intercept on the x-axis of A and also minus A on the other side, and B on the y-axis and minus B on the other side, and this point move around to give us our ellipse. If we have an ellipse, how does the Cartesian equation change from the circle? It looks quite similar. So we've still got the x squared and the y squared. I'm still going to put the 1 there as well. And we've got a squared and b squared on the bottom here. Okay, if you think about this, if we made that r squared, you'd have x squared over r squared, y squared over r squared is 1 as well. So this x squared over a squared, y squared over b squared thing is not too dissimilar to what you'd be seeing out here. How do the parametric equations change? Well, again, they're going to look quite similar. If this had a radius r, that would be r cos theta and r sine theta. But in the x direction, what's taken the place of the r, it is the a. And in the y direction, it's the b. So what's happened to our parametrics? Well, our parametrics just become that. Okay, now if a equals b, you've got a circle. No surprise, look at the diagram. If a is b, you've got a circle. And it reduces down to exactly the same Cartesian form we're looking at on the other side. Okay, so we just got to remember that's our Cartesian equation, that's our parametric equation. I'm going to be using that a lot in today's lesson. We call the distance the greatest distance across from one point through the center to another point on the ellipse. We call that the major axis, and not surprisingly we call the one in the other direction the minor axis. Notice in a circle they are both the diameter. They're both the diameter, but we've effectively got a longer diameter and a shorter diameter, okay, when we're talking about ellipses. Major axis, so the length of the major axis here is twice a, diameter would be twice r, wouldn't it? And the minor axis, we'll bring the minor axis up. Let's just do that. So the minor axis is twice b, okay, in terms of the length. So we've got major axis and minor axis. So let's have a look at some examples working with the equation of ellipse then. So we've got an ellipse here which has an equation 4x squared plus 9y squared is 36. We want to sketch it and we want to write down its parametric equations. So to sketch it to start off with, it definitely makes sense to go for the standard form that we just saw on the last slide. Yeah, the x squared over a squared plus y squared over b squared is 1. The key thing is about getting that 1 where we've got the 36 at the moment. Well, how can we make that 1? We divide by the 36. We divide down by the 36, and what's that going to tell us? Well, we've now got the 4 divided by 36, which will simplify down to a 9th, and we've got 9 over 36, which will simplify down to a quarter. So we get x squared over 9 plus y squared over 4 is 1. Remember the standard form is x squared over a squared plus y squared over b squared is 1. So a is 3 and b is 2. Okay, so that's what we've got down to, and that's where we end up with our ellipse looking like. Centre of the origin, a is 3, b is 2, from a squared being 9 and b squared being 4. Nice and easy to sketch. Write down its parametric equations. Okay, have a think for yourself at the minute. You can pause this video if you want to have a think what those parametric equations might be. I'll just give you a second to think about that, but press pause if you want to have a think. So coming back then, the parametric equations, remember we had cosine involved for the x direction and sine involved for the y direction, and the 3 and the 2 are going to be key for us. So we're going to get out 3 cos theta for the x and 2 sine theta for the y. Let's have a look at the next one. So the ellipse has got these parametric equations. Determine its Cartesian equation and sketch it. Well, we should know that in the x direction it's still going to go through 3 and minus 3 because it's 3 cos theta, and in the y direction it should go through 5 and minus 5 because that's the sine theta bit. Again, I'll give you a second to have a think about what the Cartesian equation is. So if you want to pause now, have a look back at the last question, pause now if you want to have a think about that. So let's see how you got on with that. So we've got a 3 here, a is 3, We've got a 5 here, b is 5, so that's all that this is going to change in here. A is 3, so we're still going to get the 9 there, but b is now 5, that 4 will become a 25. So let's just see that up here. That is our Cartesian equation, and our sketch, as we just talked about, how's that going to look? It's going to look like that. Difference between the one on the right and the one on the left, the major axis is now along the y-axis. Okay, the major axis previously was along the x-axis, now it's along the y-axis, and the minor axis is along the x-axis. You can always tell which direction the axes are going to be, because if A is bigger than B, then the major axis is along the x-axis. If B is bigger than A, then it's the other way around. All right, let's look at a more general ellipse then. So if you remember, we looked at shifting the center of circles. If we've got x minus 2 squared over 25 and y plus 3 squared over 16 equals 1, how does that compare where we just got x squared over 25 and y squared over 16? Have a think. Again, pause the video if you want to have a think about what that would change to now. Well, what happens? The center of the ellipse just moves to the point 2 minus 3. It's still going to have exactly the same shape. The major axis is still going to be 10 long, and the minor axis is still going to be 8 long. But that center has moved to this point 2 minus 3. Okay, we've still got a major axis that's 10 long. We've still got a minor axis that's 8 long. How could we express it parametrically, do you think? Again, have a think about what happened with the circle. I'll pause now. Pause the video if you want to have a think about it for yourself. So parametrically, we'd still get the same sort of thing going on. We need a 5 cos theta for the x1, and we need a 4 sine theta for the y1. But we need to base the x1 around 2 and the y1 around minus 3. So how the parametric becomes, it's 2 plus the 5 cos theta, and the y1 is minus 3 plus the 4 sine theta. So it's the center, the 2 minus 3, and then plus the parametric bits that we've seen before. Just like with circles again, it's very similar to circles, isn't it? Because a circle is a special case of an ellipse. We might have to complete the square to find the position of the center of an ellipse, and then find the lengths and the positions of its major and minor axes. We might have to do that first of all. Okay, we might have to do that. So let's think about how we can get this down in the first place. The key thing is, remember, we'll need to be getting it down to be x, something to do with x squareds over something, something with y squareds over something, to be equal to 1. So let's move on first of all and think about grouping the x terms together, grouping the y terms together, and how we can do it. We're going to take the 25 out as a factor in front of the x squared terms, because 25 will also go into 200, notice. And we're going to take the 4 out as a factor in front of the y terms, because 4 will also go into 16. So let's do that first of all. We'll just write it like that. Take the 316 onto the other side, so it becomes a negative. And now we can complete the squares in the x squared minus 8x and the y squared plus 4y bits. Let's do that bit. So we're clearly going to get an x minus 4 all squared, and we're going to get a y plus 2 all squared. So we've got 25 x minus 4 all squared, 4 y plus 2 all squared, still on minus 316. But what about these other bits? Where have I got those from? Well, the 25 was in front of this bracket, and if I do 4 squared, I get 16. So I've introduced another 25 times 16 on this left-hand side that wasn't there before. So I've got to do the same on the other side. On this side as well, 2 squared is 4. So I've introduced another 4 times 4 on the left-hand side. I must do the same on the right-hand side. So let's move that through. So if I keep looking at how that simplifies, then I've got minus 316 plus 25 times 16 plus 4 times 4, nicely, comes out to be 100. Okay, that comes out to be 100. But I remember I want 1 on this side. I want something to do with the x's being squared, something to do with the y's being squared. I want 1 on this side. So clearly I'm going to have to divide by 100 as my next step. 25 over 100 there will give me 1 over 4. 4 over 100 there will give me 1 over 25. So we're just going to divide by 100 and get to that standard form. Now we can say where the center of the ellipse is. So again, I'll pause for a second if you want to have a think about that. Where's the center of the ellipse and how long are the major and minor axes? So the center of our ellipse is given by these two bits. So it's going to be at 4 minus 2. The major axis is going to be in the y direction because B is 5, whereas A is only 2. So the major axis is in the y direction. The length is twice B, so that's 10. The minor axis is in the x direction, and that's going to be twice 2, which is 4. That's the end of our lesson, lesson 1. There is an exercise for you to have a go at in Dr. Frost's Maths called Ellipse 1. Have a go at that. If you need any help with anything along the way, you know where I am, you know how to let me know. Drop me a note via email or drop something into the classroom just to let me know that you need some help. More than happy to pick up with you. We'll have a look and then we'll pick up again next time. I hope that's been useful. Thanks then.